ENF. Here we go. Hey, Kiara and Matthias. Good morning. Kiara, Matthias. And good morning, Alessandra and Inessa. Good morning, Kai and Isaiah. Good morning, Ingrid and Felix. Good morning, Aslan and Stella. Good morning, Leo. I'm getting everybody this morning. I'm actually prepared. Good morning, Corey and Malta. Yeah. So, good morning, Ayala. Hope everybody's doing well. We're coming into the home stretch right before spring break. So other than this live stream, we'll just have an assignment. I think I'm going to assign you a video to watch and answer some questions on, just to kind of review. Hello, Devante is there, and Amelie. Very good. Today, I'll tell you what we're going to do. We're going to look at some, finish the ideas of medical uses, and then some other uses of radiation in our society. Oh, there's some more. Isabella, good morning, and Sophie, good morning. We've got Zach and Aaron, good morning. While we're waiting for folks, I'll sort of tell you what else is up. We're about finished with nuclear physics. After Easter break, we're going to start up with lenses, like glass lenses, and we'll learn all sorts of stuff about how to use lenses. We'll do a virtual lab that I had last year that worked pretty well. And we'll talk about the physics of your eye, which of course has lenses as well. So we'll have a 2-3 week unit on lenses when we return. There's Clara and Anton. And Sina. And Liam is here. Good morning to all of you. Timothy Pedusil is here. Bummer. Hope you get better soon, Liam. Okay, still looking for a few here. Still looking for Alessia, Tim Hartling, Paul, Avram, Allie, Julius, Linus, Lauren, and Michael and Charlotte. And from 90, looking for Corsine, Isaac, Jack, Cassidy and Alicia, Hannah, and Ethan. Let's see if any of those folks show yet. There's a Cassidy. Good morning, Cassidy. that is a good thing. Okay, let's review a little bit while we're waiting up. Okay, there's Alessia. And so we talked about there being some medical uses. So, oh, and there's a couple more. So there's Charlotte and Julius. Good, welcome. Charlotte and Julius, I got you both. That is great. They're flying in. Okay, we talked about two uses of medical isotopes, okay? One is to do what? And the other one is to do what? So maybe type in this morning, look in your notes, give me two uses of medical technology with radiation. What have we talked about so far? Because we're going to do the third one today. Imaging. Okay, thank you, Alessandra. So we can use one for imaging, for getting a picture inside the body from radioactive particles. And the other one, yeah, tracer in the body is a way to say that. To treat cancer, right, Kai? So not X-rays. No. We didn't use X-rays. No. X-rays are not a type of radiation. They're not particles flying around, okay? Nothing's radiating out to make an X-ray. An X-ray is a type of light. It's used in medicine, but it's not radiation per se, all right? So careful. We did treat some cancer, as Kiara said, with gamma rays. It was an example. We did radioactive therapy, right? Or you can say radiotherapy as well. In German, Strahlung. And the exact isotope is Inessa gave us the cobalt-60 is one example of an isotope that's used to destroy cancer cells. Right, Isabella? Avram is here. Good morning, Avram. Okay, I'm going to put that aside. I'll have to jump back and forth and mark people in. But for now, let's see if I can do that without it falling over. Yeah, more or less. We'll go like that. Anybody else? Okay, good. Then let's do our third example of a medical use. Okay, so here we go. Another type of cancer, and it's a different sort of treatment. That's why I bring it up here. It's not from outside the body, like we showed the cobalt-60 gamma rays destroying a tumor in the body. Instead, this is an internal source of radiation, and it's especially effective with throat cancer. So we got this thing it's called your thyroid in English. I think in German it's Schilddrüse. At any rate, that's where a number of people get cancer, especially if they're smokers or something, to be honest. So there's a way to treat that cancer. So here's my third way, and it's pretty specific, but it's commonly used, okay? So I'm going to say to treat thyroid cancer, and that's in the throat. With iodide. So I is our symbol, 131 is the isotope. Okay, let's see how that works. All right. Sounds kind of strange. So here's your head. I don't care about your head. Here's your throat, Adam's apple. Okay, so let's say you got, let's say this is your thyroid. Okay. Thyroid. So what happens, and the thyroid delivers hormones to the body, okay? You need a certain amount of iodine in your diet. Maybe you guys know this. You can buy salt that's iod salts or iodized salt. You buy this in the States too. And because we need a certain amount of iodine in our bodies, especially for the thyroid, okay? So it takes in this iodine. So what scientists have figured out is if there's cancer here and it's got to be destroyed, what they do is they have people, I don't know if it's either put into the blood, probably put into the blood, but they get a source internally. So I'm going to say take I 131 internally, either through the blood or digestive system, probably the blood. And I'm going to say thyroid with cancer. Okay, what do you know? No, that's a different. That's a disease, typhoid fever. Although it may have to do with thyroid. I don't think so though, Alessia. I don't. I think it's a different word. Um, what do you guys know about cancer cells? What do they do differently than normal cells? Let's see if you know this from bio. Okay. How are cancer cells different than normal cells? What do they do? What do cancer cells do that's different? Can you type something in for me if you know it? You see why I'm asking. So far I've written take iodine 131 internally and we're going to see why I'm doing this. Okay, so still waiting for some answers. They develop different than other cells and destroy the body. Yes, too, but how do they act differently? There's something special about cancer cells, something they do differently than normal cells. Let's see if somebody else knows. Yeah, thyroid, right? Okay, well, it's all right. Let's see. Okay, turns out cancer cells grow quickly, quicker than normal cells. That's one way you can figure out how to attack them in the body. So you take the iodine 131 internally and, I'll write the word and because cancer cells grow quicker than normal cells, the iodine 131 gets, I got to use a big word because I can't think of another good word to say it, gets preferentially taken in to the cancer cells. Then the I-131, this isotope of iodine, undergoes radiation and it kills the cancer cell that it's sitting in. Okay? So it's sort of like a secret weapon, you know what I mean? So then the iodine 131 undergoes radiation and kills the cancerous cells. There's a similar technique I read about with prostate cancer for men. So that is also where they'll put little radioactive uh, uh, samples in where the cancer is, and the cancer, and as the radiation happens, it destroys the cancer cells. Okay, so it's kind of it's certainly related to using radiation for killing a tumor, like we said last time. But this is an internal source, so it's operated quite a bit differently. So let's make sure we understand it, especially with my writing and everything else. Okay, so here's my throat. This is supposed to be a throat. Sorry if that's pretty bad. So there's my throat. And let's say I got cancer in the thyroid. Well, I take 131 internally, and because the cancer cells grow quicker than normal cells, the I-131 preferentially is taken into the cancer cells. Okay. Then the I-131 undergoes radiation and kills the cancer cells. This is supposed to be an and symbol. And I'll write a plus here. And kills the cancerous cells. Let's see if you got any questions or comments on that. I'll look over here in here. Uh-huh. Okay. All right. So, yeah, that's it. So there may well be other ways. I'm not up on the latest research that radiation's used in medical treatment, but at least that you got three main ways. Okay. And probably odds are good either you or someone you know is going to get cancer, and you may well learn more about one of these methods, but at least now you've had an introduction to them. And again, just a reminder, the reason I like teaching physics is I don't like just to teach you about the laws and ideas, but I want you to know where they're used in nature or in technology or in your life. And in this case, it's used in our bodies with medicine, right? So it's a pretty good use of radiation. Yeah. Okay. If we got that, we're going to continue on with something pretty different. We're going to move away from the area of medicine. So I'm going to erase my throat and other stuff here. Okay. What did I want to do next with you? I wrote this all down. Oh, yeah. I want to talk about, we have one right in Berlin, but I want to talk about devices called nuclear accelerators. What are nuclear accelerators? And I'll give you two examples. We have one in Berlin. It's over in East Berlin. It's called BESSY. I know it's funny, but that's the name of it. BASSY. It's an abbreviation for something. So BESSY in Berlin. And the really big one in the world, as far as I know, is CERN, CERN, in Switzerland. And I think it extends into France as well. It's so big. So my question to you is, do any of you know what is a nuclear accelerator? What do they do? What do nuclear accelerators do? They're used by researchers. Maybe that'll give you a hint. Ah, there you go. There you go, Alessia. Exactly. That would be a medical use you would know about. Okay, well, let's have a look then. What happens is, let's just take CERN as our example. It's a big round track, essentially. And it's got it's like this. And anyway, the thing is huge, okay? It's like, I want to say like 10 kilometers across or something like that. Maybe it's even bigger. Somebody can look it up for me, and we'll change that to the right diameter. Anyway, it's huge, and it's underground, okay? So underground, it's underground. Essentially, it's a track, if you want to think of it that way. What they do is they send particles around and around and around this thing, and then they have them collide with another particle. Bam. And then they look at the pieces. And what they found is there are what are called subatomic particles. They are smaller than neutrons and protons and electrons, okay? Little things called quarks. You might have heard of that. And that's how they discovered them and began to study them. So imagine we have a way of accelerating, that's why it's called an accelerator, accelerating particles around this circle. And they do this with a series of magnets. Okay, so these things are going really fast. We're talking really small particles. Anyway, so this is underground. So essentially, small particles are accelerated. And by the way, you can walk in this. So I mean, it's big enough to walk down, but there's nothing in the middle. It's like this track that goes all the way around, okay? Small particles are accelerated with magnets. So it's an electromagnetic effect, and we'll study that later, fourth quarter, okay? So it's one of our ninth grade topics also. So small particles are accelerated with, pardon me, with magnets. Then the particles are made to collide with other particles. So these really fast moving particles, think of them like, here they are. So they're cruising around. And then at some point, what they have are some side tracks, okay? And so you can come off on the side track and have it collide with something right down here, for example. And that's called the target. So the particles collide with particle, other particle, targets, particle, I could spell this morning. So the particles collide with other, I better write the word other. Sorry about that. Target particles. Target particles. To be really honest, then, scientists look at the pieces that form from these collisions. And the pieces are often even smaller bits of matter, subatomic particles. So scientists, they study like the size and the charge of the pieces that form, okay? So scientists study the results of the collisions. Called subatomic particles, which means smaller than an atom, right? subatomic particles. An example would be quarks, if you've heard of that funny term. There's several types of quarks. I know it sounds like something to eat, but it's not. Quarks are little tiny particles that have charge or no charge, and that they're pretty bizarre. Okay, but that's for another course, like a Lightstone's course, okay? Right. If you've had a class from Frau Ruckais, Ms. Ruckais, she's been at CERN with some students several times, so she could give you more information about that if you want to write her. She might even have something she could send you. In fact, maybe I'll find a video on that for the week. That might be cool. CERN is a pretty cool place. I've never been there, but I've flown over it. It's underground, but you can kind of see where it is if you fly over it. It's big, so you can see it from an airplane, so to speak. You can see under it. It's under some farmers' fields, but some of the facilities at the edge you can see. Yeah, so it's underground. Anyway, the one in Berlin is much smaller. It'd be like the size of half of our school, so a much smaller device. And there's different ones around the world. And this one's in East Berlin, Bessie. So we have something locally that's a particle accelerator too. It's a bit older, the one we have. Let's see if we have other questions. Yeah, types of light are given off also, Kiara, that's right, and certain materials, the subatomic particles. Yeah, exactly, Leo. They make the atoms go really fast and collide them. That's exactly what's going on. Yeah, sometimes they produce X-rays, sometimes other types of light too. And this is not a way to create nuclear energy, by the way. So it's more like just ripping things apart, Alessia, to look at the pieces, okay? Particle colliders is another name for them. Yes, you can also call them that, Leo. Good. Like maybe I'll add that. Another way to say nuclear accelerators, particle colliders. Particle colliders, which is exactly what they do. Thank you, Leo. Good-o. Good-o. Yeah, Hadron Collider is 27 kilometers in circumference. Hey, nice. And that's the one here. So 10 across is about right. About right, I think. I'd have to do the math, but something like that. Yeah, the Large Hadron Collider, the one Leo's talking about, is one that's down in part of CERN. Okay, this would be like CERN here. Yeah, good. What do they do? What do they do with those subatomic particles? Kiara, they're just trying to learn stuff about them and see what the universe is made of. They're trying to find out what are neutrons and protons and even smaller things made of. And it may not sound like, why do we care? But at a certain point, the more we learn, the more we can use those ideas for technology and other advanced things that we may be able to use for energy or whatever someday. So we're just trying to learn some basics about matter. And a lot of scientists around the world study at these places. So they're a pretty big deal in physics. That's kind of what their main thing is. Yeah. Okay. So those are particle accelerators. There's another little tidbit that I wanted to talk about with you today. Ute. And unless we have other questions there, I'm going to move on because I got another tidbit or two before we end our time together. Okay. There's a lot of cool stuff in nuclear physics, isn't there? It's a big variety of things we talk about in nuclear physics. Oh gosh. Okay, what was the next little item I want to talk about? Well, the next little item is something that might be in your apartment. Oh, got a question here from Alessia. What makes protons positively charged and neutrons negatively charged if they're made of the same things? Because they're made of different quarks. So it's not that neutrons and protons are identical. Just from our work together, Alessia, we also remember that during beta decay, I can have a neutron change into a proton and give off an electron. So I guess you could say that electron gets incorporated into the proton to make a neutron. So, and I don't know quite how that works, if it has to do with quarks or just the electron being absorbed in there, but the charge does work out. Okay, let's talk about smoke detectors. These use a radioactive isotope called americium. And I think the same symbol is AM. As a, don't worry, you're not going to get irradiated by your smoke detector, okay? As a tiny source, underline tiny source of, and I think it's gamma. You can look it up on the internet. I'm going to just say radiation. Okay, let's draw it down below and then you'll have an idea. So here's the smoke detector. Here's the electronic circuit. And then just like you learned about last year, we can have an electric circuit, right? So here's a wire. It's a little bit like the Geiger counter we talked about, okay? So here we go. Here's a wire. Here's a wire. And here's your source of americium. AM. But what that source does is it throws off particles, and the particles, maybe it's alpha, I don't know, the particles are charged, so that the charged particles, let's just make them positively charged, they complete the circuit. So this is like our power source, okay? This is like your battery. All right. So essentially, we want, as the circuit, if the circuit is complete, then your smoke alarm doesn't do anything. So it uses americium as a tiny source of radiation. The radiation completes an electrical circuit. But of course, that's not the end of the story. Let's say we have some smoke come in. So here comes some smoke. Let's say something's caught on fire and someone needs to be warned. The smoke comes in, and what's it going to do to this circuit when it hits that? Can you guess? Smoke comes in. What's going to happen to the circuit when the smoke comes sliding in here? See if you can guess, because that's really the main idea of a smoke detector. Thank you, Inessa. She's right. It breaks the circuit. And when it breaks the circuit, a bell goes off. Okay. I can't really draw that in here. I don't know what the bell looks like, but at any rate, when smoke disrupts the circuit, an alarm goes off. So if you think about it, it's pretty clever, pretty clever. So we're using a tiny bit of something to make essentially ions to make something positive, and it completes the circuit. And as Inessa said, when the smoke comes in, boom, the circuit's no longer complete, and then the alarm goes off. All right. Yeah, it breaks the circuit, right, Kiara? Yeah, good. That's a smoke alarm. So it's another use of radiation in our lives that you may not have known about. It might be in your house or apartment right now above your heads. Crazy, huh? Stuff we don't know. Something else you don't know about either, and that's the last thing we're going to talk about today, unless we got any questions on a smoke alarm. Yeah. All right. Okay. Lots of cool stuff today. Okay, the last item I think we're going to talk about today is food irradiation. See if any of you know what I'm talking about with food irradiation. Generally, it's used for fresh food. And why do you suppose they do that? Now, it used to be also very controversial. It used to be only in the United States, but then Europe adopted it. So I think a lot of the food that we get is irradiated now in Europe as well. It was a big controversy about the time you guys were born, to be honest. Okay, so what could food irradiation mean? All right. Radiation is used to kill bacteria, maybe insects too, but they're probably not outright insects. I don't think there's a lot of insects necessarily in the food we eat, but to kill bacteria in fruits and vegetables. Outright fruits and veggies. Why do you suppose they do that? Why do you suppose they do that? We're going to draw a little picture of it too, but why do you suppose they do something like that? Cena, you're right on the money. Ionizing, right? To kill germs, right? Exactly, Leo, Kiara, you got it. Yep. hmm Okay. Cena really has the idea. So it's to extend the shelf life. If you're not familiar with that term shelf life, it means how long you can sell it. So how long, essentially it's how long before it rots, okay? Before the food rots. That's really what it's about. We don't want to buy rotten food. So what this does is, imagine I got like a source here, like this, of gamma, and I think it is gamma radiation. And here, let's just have like a conveyor belt, right? A Laufbahn, I think it's called. So here's my conveyor belt. And let's have some fruit. Here's an apple. Okay. So as the fruit goes along, it gets irradiated by this gamma source. And as Sina said, yeah, it kills the bacteria in it. So the food lasts longer in the grocery store before it's got to be thrown out. Now, can you guess why? Maybe I'll make my apple red, or maybe it's a tomato, whatever you want to eat, okay? What do you suppose people were worried about? Why do you suppose some people were against this? It was actually a big deal with demonstrations and stuff at the time. What do you suppose people were worried about? Yes, exactly, Kai. That's right. Why do you suppose some people didn't like this idea? Yeah, so in general, people said like Kiara is just saying, isn't radiation bad for us? And Aaron says, clinging radiation, would radiation cling or stay on the food? People had ideas about that too. Right, they didn't want traces of it left. That's a good way to say it, Inessa. And right, Leo says the same thing there. Hmm. Right, now, there's one other, you're all correct, but there's another thing that they worried about as well. What do you suppose they were afraid of might happen to some of the good stuff, some of the vitamins and stuff in the fruits and vegetables? What do you think they were afraid of with all the good stuff, the good nutrients? What might happen to the nutrients and vitamins and stuff in the fruits and vegetables? What were people afraid of? Yeah, in a way. Okay, so essentially they're worried about either destroying, like Leo's saying, or changing the molecules of the vitamins or nutrients. So the controversy was, it's in the past, and this is the main controversy, okay? Turns out the radiation doesn't stay, so there's no real remnant radiation, luckily. So that just goes through, it's sort of like an X-ray. If you guys get an X-ray, it doesn't stick to you. It's just a form of light. Once it's turned off, you're not going to have any X-ray part of you, okay? Just like sunlight. It's not like I get sunlight and I can keep it, okay? Same with X-rays or gamma rays. A little arrow here. But the controversy was whether the molecules of vitamins and nutrients changed due to the radiation. And why do I say was? Okay, because it turns out from all the work of scientists so far, they don't find any change. So far, no molecule changes have been found. Let's call it molecular. So to be honest, the technology is still used today and we don't even hear about it because so far it looks like it's a safe technology. It does indeed kill the bacteria, so the food has a longer shelf life. It saves you and I money, right? Think of going to Aldi or Lidl and the vegetables got to be thrown out every couple of days. Well, you and I end up paying a lot more. So if it has a longer shelf life, it does save the consumer, you and I, money. And like I said, so far there's no molecular changes in the vitamins or nutrients have been found. Now, I'm not trying to sell you on this. Maybe there is some bad stuff that happens. I don't know, but it doesn't look real likely. It's been going on now for about 10, 15 years that they've been irradiating food around the EU. And before that, they started in the US as well. So it's pretty standard technology now. So weird, huh? Did you know some of your food was irradiated? It was. And again, I think it's from a gamma source. Let's see what questions or comments you have on this as well. All right. Yeah, they worried the nutrients wouldn't be there anymore, Inessa, right? Or would mutate. Yes, Kiara, right? And Charlotte says wouldn't want to kill the vitamins, right? Yeah, exactly. That the nutrients would be destroyed, Alessia. Okay, Kiara asks, are all foods treated by this? It's mainly to be honest, Kiara and everybody, food ration, it's mainly for fresh foods, okay? Mainly for fresh stuff. I don't think it's used on meats, but I don't know that. Somebody could research that and find out for me. But I know it's fresh foods like that are often irradiated. Okay. Good. Any other questions, comments from you? Well, I see our time is up and our timing is perfect. We're done with nuclear physics. Give yourself a little pat on the shoulder. Okay. Thanks everybody for your good participation. I appreciate it. I'm going to send you like a video to watch, kind of an assignment, ask a few questions about it. It shouldn't be too big a deal for the week. But other than that, I'll just wish you a very happy Easter break, and I'll see you afterwards for lenses. Okay? That I don't know, Alessia. So goodbye to everybody. Stay healthy.